Kimi K3 creates a slightly strange situation. It's an open-weight model that can compete with some of the strongest closed models on serious coding and agent tasks, but it's also so large that almost nobody is going to run the full thing on a normal computer. So what exactly did Moonshot build here? Is Kimi K3 genuinely a new frontier model? Or is this another release that looks amazing on charts, but becomes much less exciting once you actually use it? Let's start with the basic picture. Kimi K3 is a 2.8 trillion parameter model with native vision and a context window advertised at up to 1 million tokens. It's designed for more than simple chat. The focus is long-running work, coding across a large project, using tools, inspecting screenshots, working through many steps, and staying on the task without needing someone to correct it every few minutes. That already makes it interesting. But the parameter count is also very easy to misunderstand. When people hear 2.8 trillion parameters, they sometimes assume every single parameter is being used for every word the model generates. That isn't what's happening. Kimi K3 uses a mixture of experts design. You can think of it as a huge building filled with specialist teams. The whole building contains 896 experts, but for each token, the model routes the work to only 16 of them, along with shared experts that remain active. So, the model can store a very large amount of specialized knowledge without using the entire network for every step. That helps with computation, but it doesn't magically make the model small. All those experts still have to exist somewhere. Their weights still need to be stored in memory. And at this scale, we're talking about data center hardware and large multi-GPU systems, not a gaming PC sitting under somebody's desk. So no, your 16GB graphics card isn't going to run the full Kimi K3 after one clever quantization trick. That's an important distinction. Open weight does not automatically mean locally practical. You may eventually use Kimi K3 through many independent providers. Companies can inspect the weights, create specialized versions, and optimize the serving system. But running the complete model yourself is a completely different question. For most people, access will still mean using an API or a hosted service. Now here's the part that makes the architecture more interesting than just saying, it's a very big model. In a mixture of experts model, those experts may be spread across many GPUs. A token gets routed to the experts it needs, and data has to move between chips. At that point, raw computation isn't the only problem. Communication becomes a problem too. Imagine a company with hundreds of departments located in different buildings. Even when only a few departments are needed for a particular job, constantly sending large folders between those buildings wastes time. Kimi K3 tries to reduce that overhead with something called Stable Latent MoE. The simple version is this. Before the token representation is sent to the experts, the model compresses it into a smaller internal form. Less data has to travel between the GPUs. The experts can work on that lower dimensional representation, and the result is projected back up afterwards. So, instead of only asking, how do we activate fewer experts, Moonshot is also asking, how do we make the traffic between those experts cheaper? That matters because moving data between chips can become one of the biggest limits in a large model. A GPU can be incredibly fast at doing calculations and still spend valuable time waiting for information to arrive from another GPU. There's another problem too. Routing becomes difficult when you have 896 possible experts but choose only 16. The router has to keep the workload balanced. If it repeatedly selects the same small group, those experts become overloaded while other experts are barely used or poorly trained. Kimi K3 uses a balancing method based on the distribution of router scores. A useful way to picture it is grading experts by their relative position in the group rather than trusting one fixed raw score. Instead of saying, every expert above this exact number gets selected, the system compares how each expert scored relative to the others. You don't need the mathematics to understand the goal. The model is trying to remain extremely sparse without becoming unstable. So let's talk about the other major piece, Kimi Delta Attention. Normal attention is powerful because it lets the model look back across the context and decide what matters. The problem is that this becomes harder to manage as the context grows. And when you advertise a 1 million token context window, you can't behave as if every new token should repeatedly compare itself with every earlier token in the most expensive possible way. Kimi Delta Attention takes a more memory-like approach. Instead of constantly rebuilding everything from scratch, it maintains and updates an internal state. New information can correct that state, while different channels can retain or forget information at different rates. Think about someone taking notes during a very long meeting. They don't reread the complete transcript every time another person says a sentence. They keep a working summary. They update it when something important changes, and occasionally they return to the full record when they need an exact detail. That is not a perfect explanation of the mathematics, but it captures the practical idea. Kimi K3 combines these efficient attention layers with global attention. The reported design uses 3 Kimi Delta attention layers for every 1 global attention layer. That hybrid structure is the important part. The model gets an efficient running memory most of the time, but it still keeps regular full attention layers so it doesn't depend entirely on a compressed internal state. This is how Kimi K3 tries to handle very long sequences without paying the full cost of standard attention at every single layer. Then there's attention residuals. That name sounds less exciting, but this part matters. As information passes through a deep model, each layer modifies it. After enough layers, useful details from the beginning can become diluted or distorted. Traditional residual connections help preserve a cleaner path through the network. Kimi's attention residual approach goes further by allowing later layers to selectively pull information from earlier residual states. The plumbing comparison actually works quite well here. A very deep model needs more than one narrow pipe carrying everything from the beginning to the end. It needs controlled routes that allow information from earlier stages to reach later stages without being changed beyond recognition. So now, put those ideas together. You have sparse experts, compressed communication between GPUs, hybrid attention for long contexts, and improved information flow through the depth of the model. And that shows us the actual design goal. Kimi K3 isn't just trying to become larger, it's trying to make an extremely large model usable for long agent-style workloads. But does it work? The benchmark answer is often yes. The more useful answer is, it depends heavily on the task. On Artificial Analysis's AA-Briefcase benchmark, which tests agentic knowledge work such as spreadsheets, presentations, interface mockups, and other computer-based tasks, Kimi K3 scored second overall in the supplied results. Its ELO score was 1,543, placing it close to the leading model at 1,574 and ahead of several other frontier systems. That sounds excellent, but the breakdown is more informative than the headline. Kimi K3's analytical quality was very strong. Its presentation score, however, was weaker than some competing models. That's a useful warning. A model can reach the correct conclusion, perform the analysis, and complete the task, but still produce something that needs visual or editorial cleanup before you would show it to a client. And honestly, that difference matters in real work. A technically correct presentation that looks unfinished is not actually finished. A separate Fireworks evaluation covered roughly 1,030 agent tasks across software engineering, terminal work, algorithms, multiple programming languages, and legal tasks. At the headline level, Kimi K3 and the closed competitor were almost tied. On the software engineering tasks, the results were 92.4% for Kimi K3 and 92.6% for the other model. That's basically a dead heat. But underneath that average, the models behaved differently. Kimi K3 performed better on terminal tasks and legal tasks. The competing model had a clearer advantage in multilingual implementation. On algorithmic work, they were again relatively close. This is why one overall benchmark number can be misleading. Two models may finish with nearly the same average score while being good at very different jobs. One might be better at navigating a terminal and maintaining a long agent loop. Another might produce cleaner results across 6 programming languages. Which one is better? Well, what are you asking it to do? And this leads to one of the most practical ideas in the Fireworks results. Don't always choose one model for everything. Route the task. If Kimi K3 is better for terminal work and another model is better for a particular multilingual coding task, a system that predicts where to send each job can outperform either model by itself. In the Fireworks evaluation, per-task routing produced better accuracy than the strongest individual model in every category. The theoretical router sent between 72 and 96% of the tested tasks to Kimi K3, depending on the category. The remaining tasks went to the competing model when it appeared more suitable. That's probably closer to how serious AI systems will be built. You won't necessarily have one model sitting at the center of everything. You may have a cheaper general model handling most tasks, with specialized or premium models brought in only when the task demands them. Now let's slow down for a moment, because cost is where the Kimi K3 story becomes confusing. One set of supplied results showed Kimi K3 being dramatically cheaper on certain long terminal tasks, up to around 50 times cheaper on that provider's setup. Another benchmark showed Kimi averaging more than $10 per task and taking almost an hour, placing it among the more expensive and slower models in that particular evaluation. How can both results be true? Because cost isn't one permanent property of a model. It depends on the kind of task, how many turns the agent takes, how many tokens it generates, whether prompt caching is working, which provider is hosting it, and how efficiently that provider has implemented the architecture. The listed API pricing in the supplied launch material is $3 per million input tokens, $15 per million output tokens, and 30 cents per million cached input tokens. That cached rate can make a massive difference when an agent repeatedly reads the same code repository, document collection, or long system prompt. Imagine that your agent is working on a large software project. It may need access to the same files during dozens of separate turns. Without caching, you could keep paying the full input price for information the model has already processed. With caching, those repeated inputs may become far cheaper. But there's a trade-off. If the model keeps generating large amounts of new output across many turns, the output cost can still climb quickly. The AA-Briefcase evaluation recorded an average of 83 turns and roughly 120,000 output tokens per task for Kimi K3. It also averaged about 56 minutes per task. That doesn't mean every Kimi task will take an hour. It means this particular benchmark encouraged long, complicated agent workflows, and Kimi tended to spend a lot of time and tokens completing them. So when somebody says Kimi K3 is cheap, the next question should be cheap for what workload, on which provider, and with how much caching. Here's the part developers usually ask about. What is it actually like for coding? The reports in the supplied material are promising. In one real-world experiment, Kimi K3 continued working through a large software migration project with minimal guidance. It reportedly completed more than 100 subtasks from a relatively short initial prompt before the session ran into a context limit. That is the kind of long-horizon behavior developers want from an agent. Not just writing one function, not just correcting one error. It needs to inspect a project, create a plan, make changes, test them, notice failures, and continue working without forgetting the original objective halfway through. Kimi's vision capabilities also make it more useful for interface work. It can inspect screenshots, run an application, observe the result, decide what looks wrong, and then revise the code. That creates a visual feedback loop. For front-end development, games, CAD, and other visually judged tasks, this is far more useful than a model that can only read source code. A model may generate perfectly valid HTML and still create a terrible interface. Without vision, it may never realize that the text overlaps, the layout is broken, or the button is sitting outside the screen. With vision in the loop, it can at least inspect what it created and attempt to improve it. The supplied examples also describe experiments involving 3D game development and GPU kernel optimization. Those results are especially interesting because they move beyond ordinary chatbot use and into specialized engineering workflows. But there are rough edges. The full 1 million token context may not be available through every subscription or product. The model can behave differently depending on the company hosting it. And because this architecture is unusual and extremely large, serving it correctly is not trivial. A provider could technically claim to offer Kimi K3 while using context restrictions, aggressive quantization, or an inefficient configuration that produces a noticeably different experience. At launch, the supplied material also describes the model as using maximum reasoning effort by default, without the same range of reasoning controls that users may expect from some competing platforms. And even when the technical result is good, the final response or workflow handoff may feel less polished than the best closed products. That gap between capability and user experience is important. A brilliant model inside an awkward tool can still waste your time. You can have a model that successfully changes 50 files, runs the tests, and fixes the errors, but then gives you a confusing final message that doesn't clearly explain what changed. For a benchmark, the task may count as solved. For a developer trying to review the work, it may still be frustrating. There's also the open weight question. The supplied launch material says Moonshot planned to release the model weights on July 27th. Once the weights are available as described, researchers and infrastructure companies can inspect the model, improve the serving systems, build specialized versions, and create products without depending entirely on Moonshot's own API. That creates real opportunities. It means more competition, more independent research, more visibility into how a frontier-level model is constructed, and eventually, it could allow private deployments for organizations with enough hardware. Notice that I said organizations with enough hardware. For an ordinary user, private deployment may sound like installing the model on a desktop. In this case, it's more likely to mean a company running it across racks of GPUs inside its own infrastructure. It also creates real risks. A highly capable model with fewer central restrictions can support valuable engineering and scientific research. But it can also be modified or applied to harmful tasks. Open weights move more responsibility away from the original laboratory and towards the people hosting, adapting, and using the model. That doesn't make the release automatically good, and it doesn't make it automatically reckless. It means the trade-off is real. So, is Kimi K3 the best model available? Sometimes, maybe, and that's probably the most accurate answer. It may be the better choice for a long terminal task, a visual coding workflow, or a workload where prompt caching makes the economics work. Another model may be faster, more polished, better at multilingual implementation, or cheaper for a short task that doesn't reuse much context. The important question isn't simply, which model has the highest score? It's, which model solves this particular job reliably at a cost and speed that makes sense? And the wider significance of Kimi K3 goes beyond one leaderboard. The frontier is no longer moving only through closed models with secret architectures. Open-weight systems are beginning to compete on serious agent work, not just chat benchmarks and small coding tests. And the competition is shifting away from a simple question like, who has the largest parameter count? The new question is, who can make intelligence move efficiently through memory, GPUs, tools, and long-running workflows? Kimi K3 is enormous, it's imperfect, it's expensive in some situations, surprisingly economical in others, and genuinely impressive where it works. That combination is exactly why it matters. Not because one benchmark proves it has won, but because it makes the gap between open and closed models much harder to describe than it was before.